Good morning everyone. This is Venugopal, lecturer in chemistry. Right sir? Here, today we are going to discuss about hybridization. Sir, we are going to discuss about hybridization. So what is meant by hybridization? Sir, here hybridization means the intermixing of pure orbitals. The intermixing of pure orbitals to give an equivalent orbitals. To give an equivalent orbitals which are say equal in energy and equal in shape containing orbitals which are called equivalent orbitals. So the intermixing of pure orbitals to give an equivalent set of orbitals, set of new orbitals which are called hybrid orbitals. Which are called what? Hybrid orbitals. And the phenomena which is called hybridization. The phenomena which is called hybridization. Okay sir, we'll see here the intermixing of pure orbitals. Intermixing of pure orbitals to give an equivalent orbitals, a set of new orbitals which are called hybrid orbitals, and the phenomenon which is called hybridization. Okay, here sp3 hybridization of the carbon. sp3 hybridization of carbon. Here we have one of the example is ethane. What is the example? Ethane. So here C2H6. Whether number of carbons which are equal to 2 in the organic molecule, then and it is an alkane. So that's why this is said to be what? Ethane. Because eth is the root word. So that's why ethane is the name of the compound. Sir, in this ethane, we have a central atom, that is carbon. Carbon is the central atom. So what is the atomic number of the carbon? That will be 6. Right sir? What is the electronic configuration of carbon? Sir, here 1s2, 2s2, 2px1, 2py1 and 2pz0 is the electronic configuration of the carbon in which ground state. Sir, what is the ground state electronic configuration of the carbon? Which means here 1s2, 2s2, 2px1, 2py1 and 2pz0. Here, this is the valence shell. Valence shell. We know that what is meant by valence shell? Sir, what is meant by valence shell? The shell which is present outermost to the nucleus, which is called a valence shell. In carbon nucleus, we have, this is the center massive part which is called nucleus, and positively charged one, and this is the first orbit, that is n is equal to 1. And what is the electronic configuration in the first orbit? That will be 1s2. And second orbit, that is principal quantum number which is equal to 2. Right sir? Principal quantum number which is equal to 2, that is n is equal to 2. And what is the electronic configuration with respect to that? Here we have 2s2, 2p2 is the valence electronic configuration, because with respect to nucleus n is equal to 2, which is called a valence shell, otherwise outermost shell, right? So that's why n is equal to 2, which is called valence shell. The number of electrons which are present in the valence shell, which are called valence electrons. So here total number of electrons in the valence shell that is equal to 4. Total number of valence electrons which are equal to the 4. But for the formation of a bond, we require, for the formation of a covalent bond, we require number of unpaired electrons only. Number of unpaired electrons only. So here there are number of unpaired electrons in this carbon's ground state electronic configuration. We have only 2px1, 2py1 because 2s2 is paired electrons anamata. So that's why here carbon is going to promote one of the electron from the lower 2s energy level to the higher 2p energy level. How would you know 2s is lower than that of the 2p? According to n plus L values. Sir, according to n plus L values, we can say 2s is lower than that of the 2p. Sir, how? Ela? And ante chuddam. 2s energy level as well as 2p. Sir, for 2s orbital, what is the principal quantum number? So, we can say principal quantum number of the 2s subshell that will be equal to the 2. So, that's why n is equal to 2. And what is the azimuthal quantum number for the s orbital? For an s orbital, L value is equal to 0. Already we know that. For an s orbital, L is equal to 0. Then what is the n plus L value? N plus L value. So that's why 2 plus 0 that is equal to 2. Right, sir? Then 2p. For 2p orbital, what is the principal quantum number? Which indicates the main shell. So that's why n is equal to 2 is the principal quantum number for the 2p orbital. For p orbital, L value that is equal to 1. For p orbital, L is equal to 1. Then what is the n plus L value? That is equal to 2 plus 1 that is equal to 3. Sir, here there is a conclusion like this. Based on the n plus L values, 2s is clearly lesser in energy compared to the 2p orbital. Because with increasing in the n plus L value, there is an increasing in energy can takes place. So that's why 2s is lower than that of the 2p. Here with increasing in the n plus L value. For 2s orbital, n plus L value is equal to 2 and 2p orbital, n plus L value equal to 3. With increasing in the n plus L value, there is an increasing in energy can takes place. So that's why clearly 2s is lower energy than that of the 2p. So to obtain number of valence electrons which is equal to 4, here carbon can get excited. Ela excite avutundi? By the absorption of heat energy, otherwise absorption of the light energy. Absorption of energy can takes place in the form of whether it is heat energy or light energy. So by the absorption of energy, carbon can get excited. So in its excited state, here what is the electronic configuration? 2s1. And because this electron can jump from lower energy level to the higher energy level, we can see in the energy level diagram also. For the formation of 2s1, 2px1, 2py1, 2pz1. Clearly, this is known as valence shell, in which number of unpaired electrons which are equal to the 4. Because carbon's valency is 4 now. So that's why we should get number of unpaired electrons equal to 4. Right, sir? Then here we can see in this number of electrons in the valence shell which are equal to the 4. Right, sir? but here hybridization can take place because these s orbitals which are in the spherical in shape and p orbitals are dumbbell in shape, so their shapes are different, their energies are different. So to minimize the corrections, they are going to intermixing with each other. For the formation of equal in energy, equal in shape, containing an equivalent set of orbitals which are called hybrid orbitals, and the phenomenon which is called hybridization. We can see clearly here carbon which is in hybridized state. For the formation of 1s2, 2sp3, 1. 2sp3, 1. Because intermixing of 1 2s subshell and 3 2p subshells. Sir, in this we have there is a intermixing of 1 2s orbital and 3 2p set of orbitals for the formation of an sp3 hybridized orbital which contains 1 electron, like that. 2 sp3 1 and 2 sp3 1, 2 sp3 1, like that. Right, sir? Here, what is the orbital representation? We can see all are which are equal in energy, equal in shape, containing hybrid orbitals. So, what is the shape of the hybrid orbital? Here, what is the shape, sir? We can say here they are like a big loop and a small loop. All are equivalent. So here in a sp3 hybridization, each orbital can occupy with 1 electron. You can see this explanation based on the energy level diagram also. So see here, this is the energy term. Here carbon which is in ground state, so here 1s2 is the electronic configuration, 1s2, and what is the ground state electronic configuration? That will be 2s2 and 2p2. 2p2 is the electron configuration. To get number of unpaired electrons which are equal to the 4, that's why carbon can excite or promote one of the electron from the lower energy 2s subshell to the higher energy 2p subshell. So promotion of electron can take place by the absorption of heat energy or light energy. We can represent like this. Here 1s2 which is a carbon in excited state. Promotion of electron takes place from lower energy 2s2 can write as 2s1 because one of the electron ఏమవుతుంది సార్ లోయర్ ఎనర్జీ నుంచి హైయర్ ఎనర్జీ లెవెల్లోకి వెళ్తుంది by the absorption of heat energy. So 2s1 is the electronic configuration, and what is the electronic configuration of 2p orbitals? 2p2 by adding one electron, that will be 2p3. because of their energies as well as their shapes are different. Clear ga manaku telustundi sir, according to n plus L values 2s is lower energy than that of the 2p, as well as s orbital spherical in shape, p orbitals dumbbell in shape. So that's why they are going to intermixing with each other for the formation of hybrid orbitals, a new set of orbitals which are called hybrid orbitals. In this, here we have carbon which is in hybridized state. What is the electronic configuration? 1s2, and there is a formation of new set of orbitals which are sp3 hybrid orbitals. sp3 hybrid orbitals which are all are containing with one electron. So this is the energy level representation. Then what is the structure of ethane? Sir, in this ethane we have 2 carbons and 6 hydrogens. 2 carbons and 6 hydrogens. So for each and every carbon they can undergo sp3 hybridization only. They can undergo sp3 hybridization only. So each carbon contains 4 unpaired electrons which are present in the hybrid orbitals. Okay sir. And then what is the hybridization of what is the electronic configuration of hydrogen? So what is the electronic configuration, sir? 1s1 containing 1 electron, 1 unpaired electron in the s subshell. So these are all are said to be an equivalent orbitals. Once again I am repeating because to know the importance of the hybridization, right sir? To get equal in energy, equal in shape, containing hybrid orbitals. So here they are all similar in energy, but their orientation in the space is different with respect to each other, because there is a arising of an electron-electron repulsions, because similar charges are repelled to each other. Similar charges are repelled to each other. So that's why here they are going to oriented in the space. They are arranged tetrahedrally. They are arranged tetrahedrally with respect to minimize the electron-electron repulsions. Electron-electron repulsions. So to minimize the electron-electron repulsions, they are oriented in the space tetrahedrally. So we can see here for carbon, I am going to rub this. Right sir? For each and every carbon it can undergo sp3 hybridization. So that's why they are arranged tetrahedrally. They are arranged tetrahedrally. All are equal in energy and equal in shape, containing orbitals like this. For the first carbon we have like this, and for the second carbon also. Here we can represent this is the carbon, each orbital which is containing one unpaired electron. Right sir? Hydrogen contains one s electron, which is the s orbital of the hydrogen atom. Sir, here there is a formation of a sigma bond. There is a formation of sigma bond by the head-on overlapping or end-to-end overlapping. So they are going to overlap with like this manner. Etla mana shake hand istam chudandi. Right? So itla mana shake hand ichinapudu entandi here like this. There is a bond formation takes place. Right? One electron of the carbon atom and another electron of the hydrogen atom, they are going to sharing the pair of electrons like this. So that's why there is a formation of a sigma bond can takes place by the overlapping of which orbitals? A orbitals వస్తున్నాయి ఇక్కడ sp3 hybridized orbital of the carbon and s orbital of the hydrogen atom. So that's why there is a formation of sigma s sp3 bond can takes place. Like that, here we have 6 hydrogens like this manner for the formation of 6 carbon bond hydrogen bonds. All are sigma bonds because the overlapping is same throughout the molecule. So that's why there is a possibility of number of sigma bonds. 6 sigma s sp3 overlapping can take place. Right, sir? And there is another bond can formation takes place because here it is by the sp3 and sp3. Each carbon contains one sp3 hybridized orbital with one unpaired electrons. So that's why there is a formation of a sigma bond by the head-on overlapping or end-to-end overlapping. There is a formation of a sigma bond. So what is the nature of the bond? That is a sigma bond by the overlapping of sp3 and sp3. Here there is a formation of only one sigma sp3 and sp3. Right, sir? We can write like this. Here carbon bond carbon. Here the overlapping carbon bond hydrogen, carbon bond hydrogen, carbon bond hydrogen, and here carbon bond hydrogen, carbon bond hydrogen, carbon bond hydrogen. So just look like a tetrahedron. The corners of the tetrahedron we can represent like this. They are present at the corners of the tetrahedron. Right, sir? Like this. Sir, what is the bond length in between carbon and hydrogen? That will be 1.09. Carbon bond hydrogen, that will be the 1.09 angstrom units. And what is the bond length between carbon bond carbon? In a singly bonded carbons, 1.54 angstrom units. 1.54 angstrom units. And what is the bond angle? I said, they are going to formation of an equivalent set of orbitals. They are equal in energy, but their orientation is different. So they are arranged tetrahedrally because to minimize the electron repulsions. They are going to separate with each other with a bond angle that is in between hydrogen carbon and here carbon, whatever it may be, any other hydrogen carbon hydrogen carbon hydrogen carbon hydrogen. The bond angle is 109 degrees 0.2 to 8 minutes. So what is the shape? Clearly that is a tetrahedron. Tetrahedron. Okay. Here what is the conclusion? Carbon can undergo hybridization to get 4 equivalent set of orbitals, sp3, 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 sp3. And here there is a note like this. In this sp3 hybridization state, S percentage is very important. Sir, in this sp3 hybridization, what is the S percentage? అంటే ఓవరాల్గా 100 parts అనుకోండి, అప్పుడు S can get what? 100 divided by 4. So that's why S can get 25%. 25%. And remaining p orbitals which are 75% in the ratio anamata. Very important. What is the S percentage in the sp3 hybridized state? Means here S percentage will be the 25% and B will be the 75%. Thank you.